Greetings and salutations, magical chemists. Let's talk about the enthalpy of formation, or delta H sub F. This is the change in enthalpy that accompanies the formation of exactly 1 mole of a compound in its standard state from its component elements in their standard states. Remember that the tiny superscript 0, the naught, is indicating standard conditions. Standard conditions in thermochem are not STP. Instead, we are at 1 atmosphere, but we're at room temperature, 25 degrees Celsius. Let's try a few examples. The first one is writing the enthalpy formation reaction for methane. So notice we are forming exactly 1 mole of methane, and the goal is to figure out what elements we would need to make that. Well, methane has CH4, so we would need carbon and hydrogen. Carbon is a solid at room temperature, but hydrogen is a gas. And more importantly, hydrogen is a diatomic gas. So I would need 2 diatomic hydrogen gas particles. Whoops, I can totally squeeze the gas in there. And together, that would form 1 mole of methane. Now, we can do the same thing for SO3, sulfur trioxide. But because we are forming exactly 1 mole of SO3, we start to get something a little bit weird. Well, first, we need sulfur, which is also a solid at room temperature. But then, of course, we need oxygen. Oxygen is diatomic as well, and it's a gas. So wait a sec. If it's diatomic, which is O2, but we need 3 oxygens, we need a fractional coefficient. Specifically, 3 halves. So yes, it is possible to see fractional coefficients, but that's just to make sure exactly 1 mole of the compound is being formed. Now, there is something important to know about enthalpy of formation, and it's so important I gave it its own color highlighter. This is because the enthalpy of formation for elements in their standard state will always be 0 kilojoules per mole reaction. That will be really important later when we're doing calculations with delta H sub F. Okay, now you try. This time you're going to write the formation reaction for liquid ammonia. So go ahead and pause the video and try it, and when you're ready to check your answer, unpause the video. Well, for liquid ammonia, since you are forming NH3 and nitrogen and hydrogen are diatomic, you need lots of fractional coefficients for this one. Okay, now let's look at something called Big Mama's equation. This is the equation we use to calculate the enthalpy change for a chemical reaction using the enthalpies of formation of the individual chemicals involved. So this equation kind of looks pretty intimidating, but it's actually really easy to use. So let's talk about what a couple things in this equation mean. The delta H sub F are, of course, enthalpy of formation. The N is the coefficient of that chemical in the chemical reaction. The other thing that's fun in this equation is they use the capital sigma. Capital sigma is just being used mathematically. It means take the sum of all of these things. So you're adding together all the delta H's from their products multiplied by their coefficient, and you do the same thing with the reactants, and then you subtract them. That's it. So let's take a look at a given reaction, and we can see how we might write out this equation. So for this reaction down below, this is a combustion reaction. So there are actually 2 ways that you could title the delta H of the reaction itself. You could write delta H reaction, or you could write delta H combustion. And they're the same thing. You're just being specific. You're like, haha, it's a combustion reaction. You don't have to, and I don't usually, but it certainly has shown up before on tests and quizzes, so it's good to recognize what that means. Okay, now that we've got that, let's plug into Big Mama's equation. Did you notice we're starting off with our products? So we need to get delta H of formation for carbon dioxide and water and add them together. But water has a coefficient of 2. So don't forget to multiply 2 times the heat of formation of water. And so we basically take those 2 things and we add them together. And then we're going to subtract the same stuff, but this time we're going to look at the reactants, which means methane and oxygen gas. Now, of course, if we actually want to solve for delta H of the reaction, we need a table of values, and we just plug in the values. But hopefully you can see the math on this really isn't that bad. Okay. Remember how we were talking about you could say delta H of reaction or delta H of combustion? Well, it turns out there are even more subscripts than that. There's, of course, delta H combustion. There's also delta H neutralization. There's delta H solution for if you're dissolving something, and of course we know about vaporization and fusion. So there are lots of possible subscripts, but they're just specifying, well, okay, well, what kind of reaction is happening, or maybe it's a change of state. Okay, let's try some practice problems. For each of the reactions below, you're going to write down what subscript should go there. What kind of reaction is there? So go ahead and try it, and when you are ready to check your answers, unpause the video. Okay, well, the first one was an acid and a base, so that's delta H neut. And then we had a solid going to a liquid, so that's delta H of fusion. And then we have, well, of course, combustion, so delta H combustion. Okay, the second question says, circle which of the following will have a standard heat of formation equal to 0. Well, try it. See what you think. Circle everything you think would have a standard heat of formation equal to 0, and when you're ready to check your answer, unpause the video. First, hopefully you realized it can't be the compounds, right? They have to be an element. Well, there's a lot of elements, but it turns out you should only have 2 circles. Because it's not enough to be an element, you have to be in your standard state. Well, hydrogen is diatomic, and it's a gas in its standard state, so that one's 0. And bromine is diatomic, and it's a liquid in its standard state. But, fun story about mercury. Mercury is not solid at room temperature. Same thing with nitrogen. Nitrogen is not a liquid at room temperature, so those would not be equal to 0. Okay, let's try another one. We've actually already practiced this, so you should be good to go. It says write the balanced molecular equation representing the enthalpy for the standard heat of formation reaction for ethanol. That's got lots of stuff in it. So go ahead and try it, and when you're ready to check your answer, unpause the video. And there you have it. Remember to include your states of matter, because that's part of what's showing you that all those elements are in their standard state at the beginning. And as we just looked at, the state of matter really matters. Okay, we are finally ready to try some math. I know you're excited. So in this problem, they've given you some enthalpies of formation. They've given you one for CH4 and HCl in your table. And they've given you a balanced reaction and told you what the enthalpy of reaction is for that reaction. And they say, that's great. Use all that information and find the enthalpy of formation of carbon tetrachloride. Well, we need Big Mama's equation. And Big Mama's equation says we have to sum up all the enthalpies of formation of the products, subtract them for all the enthalpies of formation of the reactants, and that will give us delta H of the overall reaction. Well, funny story, we of course already know what this answer is because they told us. So now we just need to plug in the information that we have and check and see if we can solve for the information they're looking for. I will usually, before I plug in values, write down the chemicals that I'm using. Then I go back and I plug in my numerical values. You are not required to do this, but for me it seems to minimize the number of mistakes I make. So I wrote down all of my products first, and then I wrote down my reactants to subtract from them. Now I'm going to go through and use the values they gave me in the table to plug in for the things that I know. You may be thinking, but wait, it makes sense that I don't have the heat of formation for CCl4. That's what they're asking you to solve for. But they didn't tell me another one. How can I solve if I have 2 unknowns? Well, that's the thing. You don't have 2 unknowns. You know that this value is 0. 4 times 0 to be precise, which is still 0. And that's because chlorine is diatomic and a gas at its standard state. So sweet. Now we have numbers, we plug them in, and we do math. Yay, math. So I'm going to combine the terms I can, right? So I've got negative times a negative makes that a positive, and minus a minus makes that a positive as well. And so in this case, oops, I was trying to figure out what went wrong here. It's because I copied something down wrong. You probably already saw that this was supposed to be a plus sign. I was trying to figure out where my negatives went. So I have 4 times negative 93 plus positive 75 gives me negative 293. And then, of course, super easy to solve for the heat enthalpy of formation of CCl4. And so the enthalpy of formation of carbon tetrachloride is negative 96 kilojoules per mole reaction. And that's it. All right, let's try one more problem together, and then you will be masters of the enthalpy of formation. This particular problem is a little bit different than the previous one, because this one gives you all the standard enthalpies of formation that you need, and it asks you to calculate delta H combustion for the overall reaction. So this time, we don't know delta H for the reaction, but we're going to find it, using, of course, Big Mama's equation. Before plugging in numbers, it's always good to add the chemicals in your reaction first. You know what? What am I thinking? You know how to do this. You should totally try this problem. And then, when you're ready to check your answer, unpause the video. Now, you're not required to do this first step where you write out the chemicals. It just helps eliminate errors. So, whatever works for you. Once you figure out the chemicals, then you plug in the numbers. And once you plug in the numbers, you do math. Easy peasy. It's important to recognize what work would have to be shown for free response. This is it. That's the work you have to show. So there you have it. Enthalpies of formation and Big Mama's equation. So thank you for playing with all the glories of chemistry.